Hey guys, all right, this is going to be the video that you're watching while the other cohort is working on their review sheet for their test. Okay, so I'm going to do two things in this video. It's going to basically be normal distribution with a little bit of a twist, and then I'm going to have you find a value. So you're going to get two things. You're going to be finding a probability using something called a central limit theorem, and it's almost exactly like you do in the normal curve that we did in class. Okay, so that should be a simple little one extra step, and then you're back to doing exactly the same thing. So there, I'm giving you values and you're giving me back probabilities. All right. And then the second thing in the video is you're going to have to find a value off of a normal curve, not a probability, but a value. Okay. So I think it'll make sense when I start sharing it. Okay, so let me see if I can share and find my PowerPoint. Let's see if technology is going to be cooperative today. Oh, yay, it is. Okay. All right, so let me kind of remind you of something. In class on Thursday, all right, whether you were doing Zoom or whether you were actually in class, we talked about something called a normal distribution. All right, so for there to be a normal distribution, the problem's got to say the data is normally distributed. Like I would say something like IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. Or I might say men's heights are normally distributed with a mean of 68.3 and a standard deviation of 2.8. All right, so different things are normally distributed, but remember, all data is not normally distributed. Okay, so when the data says it's normally distributed and it wants a probability, remember you drew the picture and you shaded the area you were looking for, and then you went to the calculator and it did all the work. All right, well, let me show you about central limit theorem. All right, central limit theorem reminds you, what I want to remind you, all data is not normally distributed. My test grades are not normally distributed. All right, the amount of money I spend at Walmart every week is not normally distributed. All right, so lots of data, probably most data is not normally distributed, but a good bit is. But I don't want to give you the impression that all data is normally distributed, because it is not. All right, for instance, I doubt that the ages of MC students is normally distributed. I've never investigated it, but I don't think that's probably true. Okay, but here's what's interesting. Even though the ages of MC students is not normally distributed, let me tell you what I could do. I could go over to the registrar's office and I could say, will you randomly pick 50 MC students and give me their ages? So I get 50 ages. If I did an average for that group, so I added up all 50 ages and got an average of 19.56 years old. Okay, maybe that's the average age of those 50 students. Then I went back to the registrar and said, do it again. All right, now you're note, if it's random, I'm not going to get the same 50 people. So they're randomly drawing 50 people out of the 5,000 or whatever that I've got. Okay, and I get the average of that 50. I add all 50 numbers up and divide by 50, and this time the average age comes out to be a little more than 20 years old. And I go back and do it again. That should really be a 3, I guess, and that one needs to be a 4. All right, because I'm really doing it 4 times. If I kept doing that over and over, even though the individual ages of students are not normally distributed, the interesting thing is, though, these averages are basically normally distributed. They approach a normal distribution because this sample size is a certain size. Okay, so even when individual data is not normally distributed, the mean of averages of groups with some conditions will be normally distributed or will approximate a normal distribution. All right, so the averages, the average ages, the mean ages of those groups would basically be a normal curve, even though the individual ages were not normally distributed. So here's what the central limit theorem actually says in your book. It says for all samples of the same size n. So I couldn't grab 50 people one time and 30 people the next time and then 2 and then 100. So I've got to keep grabbing the same of the same size. And the sample size needs to be bigger than 30. All right. The sampling distribution of the mean can be approximated by a normal distribution with a mean of mu and a standard deviation of sigma divided by the square root of n. Now, what is that saying? Okay, here's kind of what it's saying. All right, I'm going to kind of go show you the requirements and do one. All right, here's the actual requirements. All right, it's two different things. If you know the original data is normally distributed, like IQ scores or men's heights or women's weights, the groups can be any size. There can be 3 in your group, or 300, or 50, or 2, okay? But for the group size to be any size, you've got to know that the original data for individuals is normally distributed. If the original data is not normally distributed, then your group size has to be bigger than 30. So that's why if you go back and look at this previous slide, if you backtrack, if you basically reverse this video and notice, I was grabbing group sizes of 50, okay? So if you're not sure if the original data is normally distributed, you better make sure your group size is bigger than 30, okay? So how are you going to work the problem? You're going to leave the mean the same. So the mean for the individuals is the same thing as the mean of the groups, but you are going to have to change the standard deviation. You're going to have to get a new standard deviation. Well, how do you get the new standard deviation? You take your old standard deviation and you divide by the square root of n. Remember, what's in every formula the whole semester? It's your total. So it's your group size. Now, once you do that, you're back to a normal curve. So you're going to work the problems the same way that you did before. You're going to draw the picture and use the calculator. Okay? So let me kind of do one of each to kind of contrast it and then make sure we're clear. All right, look at this problem. This problem says that women's heights are normally distributed with a mean of 63 7/10 inches and a standard deviation of 2 9/10 inches. That's what I would tell you in the problem, okay, or in the directions. Now look what the first question says. If a woman is randomly selected, find the probability that she has a height greater than 66 inches. Now, this is a regular normal curve problem, like we went over in class on Thursday. How do I know it's a regular normal curve problem? Because it says a woman. How many is A? 1. I don't have a group. All right. So I've only got one woman. And it says that my data is normally distributed. So this is a regular normal curve problem. So what do? I draw my picture and I shade the area I'm looking for. So it said, what's the probability that she has a height greater than 66 inches? So I put 66, it's bigger than this number, so it's on the right, and I shaded to the right because it says greater than. So remember what you do. You go to normal CDF, you type in your left endpoint, 66. I didn't have a right endpoint. So remember we talked about you have to fool the calculator. Nobody's taller than 9,999 inches. I think you could put 99 and still be safe, but just in case, okay? So then remember, this is my mean and this is my standard deviation. So regular normal curve, left endpoint, right endpoint, mean, and standard deviation. And my probability came out to be 0.2139. Okay, easy peasy. Now, let me kind of warn you that in your book sometimes, instead of asking you, what's the probability that a woman has a height greater than 66 inches? They might say, what percent of women have a height greater than 66 inches? If they ask me what percent, I just change this decimal to a percent. Remember how to do that. How do you change a decimal to a percent? You multiply by 100. So it would be 21.39% of women have a height greater than 66 inches. And remember, that's 5 feet 6 inches. Okay? Now, look at the difference in that problem and this problem. If 16 women are randomly selected, find the probability they have an average height greater than 66 inches. All right, so do you understand what I'm saying? I'm grabbing 16 women. I am finding the height of all 16. I'm adding them up and dividing by 16 so I get an average for the group. So I want to know what's the probability that the average of that group is bigger than 66 inches. Now, how did I know this was central limit instead of a regular normal curve? Because I'm picking more than 1. Am I picking 1 or more than 1? Okay, so when I'm trying to find the probability of the mean of a group, that's when I do central limit. So here's the only difference. I've got to change the standard deviation. I've got to go find a new standard deviation. I'm going to use the old mean, so the mean's not going to change, okay? But the standard deviation is. So I take my old standard deviation, remember they told me up here it was 2.9, and I divide by the square root of the sample size. So I'm dividing by the square root of 16. So when you take 2.9 and you divide by the 4 by the square root of 16, you get this number. So I'm going to use this number for my standard deviation. Then I'm back to a regular normal curve. My first step, draw my picture. There it is. What goes in the dead center of a normal curve? The mean. I want it greater than 66. So I put my 66, I shaded to the right because it said greater than. So I go to my calculator, normal CDF. So I put in my left endpoint, had to fool the calculator for my right endpoint. My mean is the same. Here's the only difference. My standard deviation is not 2.9. My standard deviation is this new standard deviation, 0.725. And when I did that, my probability changed dramatically, 0.00076. Okay? Now I wrote down here, this is what was on my screen. But remember, this is switching to scientific notation. If you see an E and then a number, this is how many places you move the decimal. So because it was negative, I had to move it to the left. So I had to move it 1, 2, 3, and 4. So that's where I got that number. Okay, so I want you to notice something. How am I going to know if it's central limit? It's central limit when I'm doing the probability of the average of a group. So more than 1. So notice the pictures look the same. The left endpoints are the same. The right endpoints are the same. The means are the same. The only difference is this standard deviation and this standard deviation. So when it's central limit, you take your old standard deviation, and I messed something up. So you divide by the square root of that sample size and you use that new standard deviation. So other than that one fix, it's just like the normal curve problems you were working in class on Thursday. Okay, so that's the one extra step. The one extra step is that you have to change your standard deviation. Now I do want to remind you, I said that the sample size need to be bigger than 30 most of the time, but this sample size isn't bigger than 30. So why was it okay? Remember what the sheet says, the steps before. If the original data is normally distributed, then your sample can be any size. So being smaller than 30 is okay if you know for sure that your original data is normally distributed. Okay, let's go work another one to make sure that we're okay. Now look what this one says. It says soda cans are filled with an average of 12 ounces. That's got cut off a little bit, so that's a 12, and a standard deviation of 11/100ths of an ounce. So if 50 cans are randomly selected, find the probability that their mean weight, all right, is between 11.9 ounces and 12.05 ounces. So, you know, the little can says it holds 12 ounces, but they, you know, it's not always going to be exactly 12. So I want to know what's the chance if I pick 50 cans up and I weigh all 50, and then I find the average weight. I add those 50 weights up and divide by 50. What's the probability that that average weight is between 11.9 and 12? Now, how did I know that this was central limit? Because it's asking about the probability of the mean of a group. I didn't get finished, okay? So the key is this 50 cans. It didn't say 1 can, didn't say a can, it said 50, all right? So that's a group. So does everybody understand that my sample size, my total is 50? Okay, So because I decided central limit, I've got to change my standard deviation. So I go up here and find my old standard deviation. There it is. But I've got to divide by the square root of 50. Now, don't do this. Don't find the square root of 50 and then round that off and then round off again. You'll get too much error. Just type in your calculator, 0.11 divided by the square root of 50, and then round off. Okay? Don't round off too soon or you're not going to get the answers in the back of the book. Okay? So now I'm back to a regular normal curve. All right? I draw my picture. Boom, boom. What goes in the dead center of a normal curve? The mean does. And I didn't change the mean. The mean was 12. I keep the 12. What I changed was the standard deviation. So I want it between 11.9. So I put my 11.9 is smaller than 12, so it's on the left, and 12.05, 12 and 500. So that's to the right because it's bigger than 12, and I shaded between them because it said between. Okay? So I go to the calculator, normal CDF. Remember, left end point, there it is. Right end point, there it is. My mean is the same. Oops, but my standard deviation, I did not use this 0.11. I used that 0.0156. Okay, and I got 0.9993. Okay, now, see, it didn't say anything about my original data being normally distributed. The words normally distributed are nowhere in this problem. So how did I know that it was central limit? Because I'm asking about the probability of the mean of a group. And then notice, because I didn't know if the original data was normally distributed, my sample size had to be bigger than 30. So if this had been 15 instead of 30, I would not have been able to work the problem. I'd have said not enough information. Okay, so if the original data is not known to be normally distributed, you have to have your sample sizes, your group sizes must be bigger than 30. So do we understand that when it's a central limit, you've got a group, okay? And you just change the standard deviation, then you're right back to a regular normal curve. All right, now I do want to go back and show you one thing real quick before I move on to the next thing. I want to make sure this makes sense to you. Go back to this one. All right, and again, this was one woman. Now remember, this is about, I want to know what's the probability she's over 5'6", because 66 inches is 5 feet 6 inches. Well, there's almost a 20% chance that a woman's going to be over 5'6". Okay, so that's not unusual. But think about it. This is the probability that the average of 16 women is more than 5'6". It's highly unusual. Now remember, the author's definition of unusual is when the probability is less than 0.05, and that number is way less than 0.05. Because think about it. For the average of the group to be taller than 5'6", I got to accidentally pick a whole bunch of people that are taller than 5'6". And if I had somebody a lot shorter than 5'6", I'd have to get somebody like giant tall to kind of even that out. So that's why these probabilities are so dramatically different. Finding one girl that's pretty tall, not so unusual. Finding a whole bunch at once, very unusual. Okay? So that's how we do central limit. It's only when you've got a group and you change the standard deviation, then you work it like a regular normal curve problem. All right, so you're going to work some problems like that. Now, the reason I did this second is because it was so close to the normal curve. Now, let's talk about what we're going to do next. All right, next, instead of giving you the value and you giving me the probability, I'm going to reverse it and give you the probability and you're going to give me the value. Now, what do I mean by that? Look what the example says, then we'll go back up here to the steps. The example says IQ scores, I know you're tired of them, but oh well. IQ scores are normally distributed. The mean is 100 and the standard deviation is 15. I'm not going to expect you to remember that. I'm going to tell you. It says, what IQ score separates the top 10% from the rest? See, nowhere in that problem does it say find a probability. It says, what IQ score? See, that's a value. Is it an IQ of 100 and 140? What IQ is it? So when they want a value, again, the first step is you draw a picture. But this time, to work the problem, you have to shade the area to the left of the value you're looking for. Now remember, when we were doing probability, let me go back and show you. When we were doing probability, sometimes we shaded to the right. Sometimes we shaded between. Sometimes we shaded to the left, but a lot of times we didn't. But when you're trying to find a value, you have to have the area shaded to the left. Then you go to the calculator. You're still going to go to second Bayes, but this time you're not going to pick normal CDF. You're going to pick this thing called inverse norm. For most of you, it's the third one down. Now, let me tell you why it's called inverse norm. If you know anything about algebra, you know that with functions, domain comes in and range comes out. An inverse function switches that. So what was coming in is now going out, and what was going out is now coming in. So the input and output switch on inverses. Well, a few minutes ago, it asked you something like, what's the probability that somebody is taller than 66 inches? So the 66 inches went in, it was the input, and the probability came out. So now we're reversing it. We're going to put the probability in and get the value out. So that's why it's called inverse norm. Now this time you got to remember, it wants three things. Now remember back with probability, it wanted four things. On probability, it wanted the left endpoint, the right endpoint, the mean, and the standard deviation. The way the calculator's programmed, it doesn't want endpoints, it wants area to the left. That's why you've got to shade the area to the left, because that's what the calculator wants. And then the mean and the standard deviation. Okay, so let me kind of show you what we would do. I draw my picture. So I drew my picture, boom. What goes in the dead center of a normal curve? The mean. So I put the mean down. Now it said, what IQ score separates the top 10% from the rest? Well, where would the top 10% be? Would that be way over here or way down here? Do you see the top 10% would be right here? So I want to know what number is right there. So that's why I put X with a question mark. Is it 103, 195? What's that number? All right. But see, here's the key. I have to know the area to the left. But now think about it. If 10% is above it, what percent's going to be below it? Do you see it's going to be 90%? Okay. So if it's 10% above, all the rest, 100% minus 10% gives me 90%. It's got to be below it. But how do you write 90% as a decimal? Wouldn't you put 0.9 or 0.90 if that makes you feel better? So that's the area to the left. So that's what I would type right there. 0.9 or 0.90, that's my area to the left of the value I'm looking for. And then there's my mean and my standard deviation. And I rounded to a whole number because IQ scores round to whole numbers. We don't have partial, numbers on an IQ. Okay? So let's go do another one and make sure. One more and then we'll be finished. All right, look what it says here. It says men's heights are normally distributed also, but their average is not 63. Their average is 68.6 inches. So 5 feet, like 8 inches is kind of the average height, with a standard deviation of 2 8/10 inches. Now this one's kind of a little more interesting. It said what heights, should say separate, let's make that grammatically correct, the shortest 5% and the tallest 5% from the rest. So it's looking for more than one height. So first thing you do is draw your picture. Remember, boom. But now look what is unusual. I want to know what heights separate the shortest 5%, that'd be over here, from the rest, and the tallest 5% from the rest. So does it make sense why the tallest 5% would be up here way above average and the shortest 5% would be down here way below average? So I want to know what's this height and what's that height. So I need to know what that height is and I need to know what that height is. I mean, is it 56 inches? Is it 62? I know it's smaller than 68.6. I know this one's more than 68.6. Now, when you're looking for two values, it's really going to be better to do separate pictures. Because remember I said you had to have the area to the left shaded. So I'd probably go do this one first because it's the quickest. What's the shortest 5%? Well, that would be over here. Now remember, how do you write 5% as a decimal? Doesn't it 0.05? So again, I would go to inverse norm. This is my area to the left. See, there's my value, and the area to the left is 0.05. So I put in 0.05. That's just my mean and my standard deviation that they gave me in the problem. When I hit enter, I just rounded it, 63.99 inches. So this number right here would be 63.99. Now, what about the tallest 5%? Now, do you understand that the tallest 5% would be right there? But why didn't I shade that? Because remember, when you're trying to find a value, you have to have the area shaded to the left. Now, what do I know? Well, if there's 95% here, what's 100% minus 5%? Wouldn't that give me 95%? And then when you change that to a decimal, won't it be 0.95? So you have to have the area shaded to the left. So there's my area shaded to the left, the 0.95. There's my mean. There's my standard deviation. I get 73.21 inches. So this is the height that separates the top 5% from all the rest. And this is the height that separates the bottom 5% from the rest. So when you're wanting to find a value, you're going to use this inverse norm. And you have to have the area shaded to the left because that's what the calculator wants. Okay, so that's all we've got. So I'm going to kind of stop sharing this screen. All right, you've got your homework, but I really wouldn't worry about the homework for this video probably till after my test on probability. So I would kind of do double homework after my test. Until my test, I'd want to study for my test. Okay, so try the homework problems. If they don't make sense, then after your test, we'll go over some of them in class. All right, study, study, study.